Okay, great. So first of all, belated Happy New Year to you guys, and warm good morning to you all, or I should say very cold good morning today. So anyways, yeah, so welcome you all to this new semester and for this first class of your semester. This is your first class today, right? Or did anyone have an 8 o'clock class? No? 8 o'clock class. Okay, awesome, great. Anyway, so as is the customs, let me just give a brief introduction and then we'll get started. So you should know that this course is E613, high frequency analog circuit design. I'm hoping that everyone seated here is for this course. If not, this is your last chance to leave. Otherwise, I'll lock the room and I'll not let you leave. Okay. Hopefully, everyone is for this course. Okay. Great. So yeah, to give an introduction, of course, I mean, I usually say this, the same thing I keep saying. I mean, over the last few years, I'm sure the term semiconductor chips are definitely one of the most commonly seen terms in newspaper articles, media outlets, TV channels, etc. To that extent, that to such an extent that the general public is kind of aware of what this is, right? And so much so that 30 years back, let us say, if someone came up to you and asked, what do you do for a living? And you say, hey, I'm a chip designer and I design chips for a living. There was a very high chance that they thought you worked for a company like this, right? Designing chips like this. But luckily, hopefully now it is no longer the case. The general public is kind of aware of what these are. These are semiconductor chips, integrated circuits, blah 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 blah. Very crucial for our country's growth, etc. So if these chips are essential for our country's growth, obviously if you build your expertise in chip design, you will bring a lot of value to the country. It's as simple as it is. And by the way, how many of you here have heard of SPICE simulators before? Heard or used of SPICE simulators? Right? Everyone has at least heard. So then I usually make this following pun. So why are Indians good at circuit design? Well, because Indians can handle a lot of spice, right? And India is home of spices. So again, although this is just a pun, the fact still stands that even globally, a good fraction of circuit designers are Indians and are from India. Okay, and if you just take chip design as such, you can have completely analog circuit design or a truly digital circuit design. Now, the main difference I see between these two extremes is the following. As a digital circuit designer, you will never get to work with transistors. You never get to have the feel for a transistor, right? Because you always work at a higher level of abstraction. You write Verilog or VHDL or some code, give it to a tool and let the tool do a magic and give a layout back to you. But that's not the case when you are an analog designer, right? For example, here I am showing the top level layout of a chip I designed several years back. This has both analog and digital components. So which one do you think is a digital block? The left one or the right one? I mean, there are two things you can see, right? Or I would say two halves, one here and one here. Which of these two do you think is a digital block? Yes. Left one. Okay, how many for right, how many for left? Okay, how many think it is the left one? So, so how many think it is the right one? Okay, so people who thought it was right, you are right. The right portion is the digital block. Okay, and frankly speaking, I have no idea what each transistor here is and what their sizes are, etc. All I did was to describe this entire functionality through Verilog, gave it to a set of tools, followed a bunch of design flow, and then the tool threw out a layout back at me. That's all I did. Whereas this one here is a fully analog block. So which means each and every transistor, resistor, capacitor in this design has been particularly designed by me. I've chosen their sizes, values, everything, so that the overall performance of the circuit is met, right? So, and even I've chosen the physical location of where each transistor, each capacitor has to be present, again taking into consideration the overall performance of the circuit. So this is the level of thing you play with as an analog circuit designer. So now, of course, here if you see in the digital block, the layout is all done by the tool. So there are hundreds of thousands of transistors here maybe, I don't know. And in general, you will find that the number of transistors in an analog design is several orders of magnitude smaller than what you will find in a digital design. But actually, that's what makes things exciting and interesting, right? Because the number of transistors we have is very small. As a designer, you should have a clear understanding of what the role of each transistor is in the particular circuit. You can't think that, hey, I have less number of transistors, I'll write KCL, KVL everywhere, get a bunch of equations, and I'll get a 100-page equation, and you'll never be able to do it. And remember, if it were just up to solving things and analyzing things, computers are exceptionally better at it. As an analog designer, the value you add is the intuition and qualitative understanding of what is the role of each transistor in a circuit. What is it? How is it affecting the final performance of my circuit? So what will happen if I change the dimensions of a transistor, if there is some non-ideality in the transistor, so on, right? That kind of qualitative understanding and feel is what you should develop, and that's what will add and that value is what will be valued in the industry. Okay, so I hope that through this course you kind of learn and develop that skill. So then I'll just mention about a couple of things. Instructor is me, I'm Ashwin, in case you don't know, and the TAs of the course are Abhishek and Jansi. So if you have any doubts in the course, you can contact the TAs or me directly. So we'll be happy to help you. And I had also mailed the first course handout a couple of days back. Hopefully everyone received it. So please go through it. Will have all the relevant things for the course. Now, the couple of things I want to highlight here are this. The grading policy is this. So we'll have mini quizzes and design projects counting for 45% of your grade. Midsem and endsem for 55%. Okay. And there will be 5 mini quizzes in the course. The schedule of those mini quizzes I'll put out today evening or tomorrow morning at the earliest. Again, all these announcements I'll put it in the MOOKit. So if you're not added to the course MOOKit page, so please drop me a mail today immediately, I'll add you. Okay, because all the important course announcements will be posted in this MOOKit page. Yeah, and the thing is, as I told, I'll have 5 mini quizzes. And in general, if I have n mini quizzes, I'll take the best n-1 out of those n mini quizzes for your evaluation. And yeah, and also other thing I forgot to tell. So in the first couple of months, I plan to have 4 extra classes during Saturdays. I mean, these are not technically extra lecture hours, because if I take those 4 lecture hours, I will not take classes in the last couple of weeks in the semester. I'm sure last couple of weeks everyone is busy with everything. So I try to keep that last couple of weeks free. If that has to happen, I need to cover those lecture hours earlier. Right? So total number of lecture hours will be 39. I'll just take few of them in the first couple of months. Again, the schedule of those extra lecture hours will be posted in the MOOKit page. So make sure you are added. And there will be 2 design projects. One to be submitted after the midsem and one before the end semester. Again, you'll get to know the details soon. And yeah, I do not want any kind of malpractice in the course, right? If anyone is found to be involved in any kind of malpractice, will be directly reported to DOA, and your final grade points will be reduced by 1, 2, or 3 grades, whatever I feel is fit. Okay, so please, don't do it. And I would say this is your reward for your dishonesty, and this reward will be given for both the person who is copying and the person who helps copy. So both the transmitter and the receiver will be given the same reward. So please don't do this. Be honest and do your best. You will be great. Okay. So yeah, I think I don't want to talk about general things. So let's get started with the course. So the first 3 or 4 lectures will typically be a recap of what you have already seen. So as you know, this is a second level analog circuits course. So it's assumed that you have taken a basic analog circuits course before, right? So whatever I'll be covering in the first 3 or 4 lectures should essentially be like a recap, something that you have already seen. It should essentially be a brush up for you, right? Maybe some of them might be new what I covered today, but generally it should be a recap. So it should be like, watching the highlights of a cricket match, say, last India-Australia test match. Should exactly know who's winning, who's getting out in which ball. And you should not be shocked at the end to see that India lost the test match. So should know what's each. So yeah. And at any point, if you have any doubts in the lecture, please pause and get it clarified. So usually say that this is a long lecture, or if you don't understand something in the beginning, you'll not be able to follow the rest of the lectures. Then it will be like watching a Korean TV series without any subtitles. Okay, you will not follow anything. So make sure subtitles is turned on. The subtitles is me clarifying things to you. Okay. So please feel free to interrupt me at any time. Great. So then let's get started. So the main point of focus in this course will be understanding this triangular block. Oops. And what is this? It's an op-amp. Easier to draw than to design. Or maybe after the course you'll find it easier to design than to draw, maybe. I don't know. But anyway, so if let us say this has a gain of A and this is V1 and V2, what is the output voltage? A times V1 minus V2. And ideally, what do you want the gain of the op-amp to be? Infinite. So that begs the question, why on earth will I need something that gives an infinite gain? Because if I just have a block with an infinite gain, any non-zero input I feed, what will be the output? Ideally infinity, but in practice you will have supplies. So it will get saturated to the supply. So why do we need a block that gives an infinitely large gain?
It can be used in negative feedback.
Yeah, so idea is, as he's pointing out, remember that we have the classic negative feedback model. Let's say this is the forward gain and this is the feedback factor. I've not drawn it neatly, but it's okay. Everyone has seen this before. So if this is V in, what is V out? Okay, I'm hoping everyone has seen this, whatever drawn before. It should not be new to you. Fine. So what is the output here? What is V out? Yeah, V in times A by 1 plus A times beta. I'm sure you have taken some control theory course. You would have seen this. This is a classic negative feedback model. And here is where you see that I have to take the difference between two quantities, amplify it. And here if the gain tends to infinity, that is if A tends to infinity, what will this tend to? 1 by beta times V in. So if let us say beta is chosen to be say 0.1, what will be the gain? 10 times, right? So the idea is, so that the reason to have an infinite op-amp is that you can use it in a negative feedback loop to get a finally precise gain, right? That is the merit of having an infinite gain. Otherwise, it has no use. The actual merit comes because of the fact that you can use it to make negative feedback systems. And negative feedback systems are, I would say, one of the main reasons why the world is functioning as we know it. And it's a negative feedback. Your body is keeping you alive based on negative feedback, because your body temperature is regulated based on that. Your blood glucose level, everything is stabilized by your body using negative feedback. And the usual example I give for negative feedback is this. So let us say when you are trying to speak, right? You want to speak at a particular loudness level so that the opposite party can listen to you and hear you, understand you properly, right? And if you think about it, this task is accomplished by negative feedback, right? Because say you are speaking, this is basically a speaker, but this is you speaking. You want to make sure that you are speaking at a particular loudness level. So what happens? What you are speaking is heard back by your ears, right? So of course I cannot draw your ear here. So instead of drawing that here, I'll just say it's something. So this is sensed back by your ears, and then your brain kind of compares this with this. Say this is your brain, and it looks like a cloud, but then how to draw a brain? Okay, let's say this is the brain, and your brain then instructs you to either speak at a higher loudness level or lower loudness level, so that it's kind of stabilized, right? That's what happens. And a more relatable example is an extension of this. see, I'm sure everyone hopefully has experienced this. If you are having good headphones covering your ears, you tend to speak less louder or more louder? More louder. And why do you think that happens? Based on this model, can you tell me why that happens?
Because the feedback is less.
Yeah, I mean, so as he's saying, what happens is, now if you are having headphones, your ears are not exactly sensing what you are speaking. There is an attenuation in this path, right? So let's say, for example, that is 0.1. So which means the output will be how much times the reference level? You will be speaking 10 times louder than what you actually intended to speak. That's essentially what's happening here, right? Okay. So the point of this course is to learn how to make op amps so that it can be used in negative feedback systems. Okay. And the moment I say negative feedback, what is something that you think can go wrong in a feedback system? When I say negative feedback, what is something that you think can go wrong? Stability. I'm sure everyone is aware that if you're not careful, a negative feedback system can become unstable, right? So the point of this course in a single line is I would say to learn how to design op amps on integrated circuits so that you can use it in negative feedback systems, ensuring the stability of the loop. Okay, that's the single line description of the course. Okay, cool. So now for making the op amps, we use transistors. They are the devices we have, and in this course we will be using MOSFETs. So I'm sure everyone has seen MOSFETs before, and let's say I have an NMOS like this. This is the gate, drain and source, and I'm sure you know you have the complementary version, the PMOS transistor. This is the gate, source and the drain. Okay, so let's take an NMOS first. You guys know what are the different regions of operation. Let's quickly go through that. So if I were to operate the transistor, the NMOS transistor in saturation, what is the condition? Yeah, first of all, what can you say about the VGS? Should it be smaller than the threshold voltage or greater than the threshold voltage? Okay, great. What about the drain to source voltage? Yeah, and okay, let's not use overdrive it, let's just write it fully. So this should be greater than what? VGS minus VTH. And if this happens, what is the drain current in the transistor? What is the equation for the drain current? Half mu NC OX W by L. And this is one, I mean this is like the very simplest version, and in practice the current also slightly depends on the drain to source voltage. Yeah, and that you can account it by adding this factor 1 plus lambda times VDS. Cool. Just keep this here. So now let's say I make a small change to VGS. Do you think the drain current will change? Drain current obviously has to change. And how is the change in the drain current related to the change in the VGS? Yeah, or I would say, is it related in a linear fashion or a non-linear fashion? Huh? I mean, yeah, strictly speaking it is non-linear, but remember that as long as you are interested in small changes, any non-linear curve you take, if you zoom in close enough, it looks like a linear curve. So that's why you approximate the change in the drain current to be a linear function of the change in the VGS. And that's what gives rise to the small signal linear model or the incremental circuit So if I were to draw this, it is gate here, drain and source. So in response to a small change in VGS, you have a current flowing from drain to source. So that is modeled by a voltage controlled current source like this. So let us say this is GM VGS. And similarly, if there is a change in the drain to source, even that kind of impacts the drain current. So that is modeled by introducing a resistor here that draws an appropriate amount of current in response to change in the drain to source voltage. So we'll call this the R0 of the transistor. So remember that the GM or the transconductance is first derivative of the drain current with respect to VGS. So if I differentiate this with respect to VGS, what do I get? UNCOX W by L? Yeah, VGS minus VTH. Right. Now in terms of the drain current, what is the transconductance? Something you should have known, or I mean the idea is now I am trying to replace VGS minus VTH in terms of ID. Do a simple, like algebraic manipulation. You will square root of 2 ID times mu NCOX W by L. And I mean you can also show that this is indeed equal to 2 times ID by. It's all simple manipulation of different expressions. So one thing you see, for a given VGS minus VTH, the GM is proportional to the W. But if the drain current is fixed, GM is proportional to square root of W. Right? So just have that in the mind. And okay, so and what about the R0 of the transistor? How is it? I mean, what is the expression for R0? Remember? 1 by? Yeah. Remember that R0 is essentially the first derivative of drain current with respect to VDS, or I would say the inverse of that. And you do that, you will find this to be equal to 1 by lambda T. Great. So now we have seen in the saturation. So let's say let's see what will happen if I don't, satisfy these two conditions. So let's say my VGS is greater than VTH, but drain to source voltage is smaller than VGS minus VTH. What is the region of operation? Linear or triode? Let's say it's linear region or triode, whatever. Right? And what is the drain current here? Anyone remember? UNCOX W by L. Okay, VGS minus VTH times VDS. Yeah, minus VDS square by 2. This is correct? Yeah. Cool. Oops. So once again, if I make incremental changes to VGS, the drain current will change or will not change? It will change. And again, how is the change in the drain current related to VGS? Is it linearly related or non-linearly related? Again, linearly related. Again, this can be a non-linear equation, but as long as you are interested in small changes, you approximate the non-linear curve as a linear curve. So if I were to again draw the small signal model, how do you think it will look like here? Okay, what I am saying is I know that if I make small changes to gate to source voltage, the drain current is going to change. And you guys told that the change in the drain current is related to change in VGS by a linear relation. If I were to capture that through a circuit model, how will it look like? I have gate, drain and source. Right? Now in response to VGS, what do I have? In response to VGS, what is happening here? Current is flowing. So how is it modeled now? How is a resistor? Where do you want to add a resistor? I am having, yeah. remember that again it's the same thing. I have, this is source. In response to VGS, I have a drain current. So drain current has to be between drain to source. So I need to have a dependent current source here. So again Gm times VGS. Right? It is some Gm. I mean the value of Gm is going to be different, right? And similarly, if I make changes to VDS, the current will change or it will not change? It will change. So how is the change in the ID related to change in VDS? Linear or non-linear relation? Linear relation. So in response to change in VDS, I am having a current flowing here. How do you model that? Yeah, the voltage is changing here. In response to this voltage, I am drawing a current, and that is easily modeled by a resistor, and that's what you do here. Right? So this is some R0, let us say. Great. Is this clear? So let's quickly write Gm. Gm is once again the first derivative of the current with respect to the gate to source voltage. If I differentiate the current with respect to VGS, what do I get? Nu and Cox W by L into VDS. Right? So yeah, let me ask you the question now. So in which region do you think I should operate my transistor for in analog circuits, typically in which region do we operate the transistors? Yeah, why not in triode?
Because the drain to source voltage is lesser when we compare with the transconductance of saturation.
No, I mean look at okay, you're saying GM is smaller.
GM is smaller.
Why? I mean look at the GM expression. In saturation it's mu and Cox W by L, VGS minus PTH, and here is VDS. I mean I can have a case wherein VGS minus PTH here is say 0.2 volts, and I can have a case wherein VDS to be 0.2 volt, whereas VGS minus PTH has 0.5 volts. See, what I'm saying is, in this case, when I'm operating in saturation, I can have VGS minus VTH to be, an example, 0.2 volt, and keep VDS to be 0.5 volts. This in saturation. Whereas here, I can do the same thing. I can have my VDS to be 0.2 volts, whereas I can keep VGS minus VTH as 0.5 volts. It is in triode, but the GM value is still same in both. You get the same transconductance in both saturation or in triode or linear region. So then why not we bias the transistor in triode region? Less supply for the same gain, meaning?
Like in that case, we are giving less voltage for the same voltage at the gate, but there we are giving a higher value.
No, I mean, okay, if you think about it, see, a transistor is connected like this, right? Typically, the supply is from drain to source, loosely speaking. So lower VDS, it's actually better for you, correct? In saturation, you want a higher VDS. If you're talking about supply, in fact, I would say this seems to be better, right? VDS is smaller.
For a same given overdrive voltage, if we compare the VDS values, which is less,
that's okay, right?
Overdrive and greater than, then we prefer.
That's okay. I mean, so yeah, I mean, it's just a matter of, like I'm getting, this requires a slightly higher overdrive. I can use it, but we never want to use a transistor in triode region. Why?
Because output is dependent, current is dependent on the output.
Yeah, correct. So
there will be some negative feedback.
Why negative feedback?
There will be some feedback.
I mean, there is always, look at the small signal model. It is both identical. Right?
Because we wanted the current to be only as a function of the input parameter.
Correct. Why?
The current to be as a function of the output parameter.
That's correct. But why?
The reason is that anyhow, suppose you are going to develop an amplifier, the input signal that to be amplified will be applied at the gate, which will be a part of the input.
Yeah, okay, you're hinting at the right thing, but see, that is one line of thought, right? I understand that's correct. But can you map that line of thought to what we are discussing here?
Because of lower R0 value.
So you are talking about R0. Let's do that, right? See, Everyone knows that the intrinsic gain of a MOS transistor is what? GM times R0 or RDS. I'll use R0 because I don't want to write DS. R0 is easy. GM times R0 is the intrinsic gain, because that's what you want for an amplifier to do. Any changes in my gate voltage, I want a large fraction of the voltage to appear here. Imagine like a tap, right? I just open a tap a little bit, I want lot of water to flow. So if that has to happen, let's look at GM and R0, right? But when I look at GM, both are similar. Fine, is that clear? GM in both linear and triode can be made similar. There is no issues. Can you tell me what is RDS for this transistor? I mean for this case. How do you find R0 from this equation? I differentiate ID with respect to VDS and inverse it, exactly. So can you do that? Can you tell me what you get? This is 1 by something. I'll write it as inverse. Nu and COX W over L. Okay, I need some more space. VGS minus VTH minus VDS. Fine. 11th standard calculus done. So this is inverse. So now let's look at the intrinsic gain in both cases, right? So what is the gain here? GM times R0. Let's say I use this value of GM R0. If I take product of these two, what do I get? If I take product of this, it's 2 by lambda times VGS minus VTH. Right? And I mean, typically, as you know, lambda can be 0.1, 0.01 or something. VGS minus VTH is, let's say, hundreds of millivolts. So as you see, this will be much greater than 1, right? Now let's do the same thing for triode. So if I take product of these two, what do I get? VDS upon VGS minus VTH. Fine. I'm just taking the product of these two. Oops. This is what you get, right? Do you think this is greater than 1 or less than 1? Okay, maybe we can write it in a more understandable form. I'll divide the entire thing by VDS. Okay, so it's 1 by VGS minus VTH by VDS. When you are operating in triode region, this factor is greater than 1 or smaller than 1? VGS minus VTH is greater than VDS. So this term is greater than 1. So this term will be, no, this term will be greater than 1 still. Fine. I mean, or I will say, yeah. So this will be, typically you will find this to be less than 1. Right? That's the reason why you don't use it. Right? Again, as one of you had pointed out, I mean, even in your earlier analog circuits course, you would not have started with a MOSFET, right? You would have started with the goal of making an amplifier. To get power amplification, you would have derived what is the required two-port parameters characteristics. And if you recollect and jog your memory, you will find that the output characteristics of the two-port network should be something like this. The output characteristics of the two-port network translates to ID VDS for a MOSFET. You want to make sure that the Y22 was 0, that is, you should have a flat region. And of course, for passivity, you wanted to make sure it kind of also. You wanted this slope to be really small, ideally 0. And if it's not 0, at least have a very small slope like this. So it makes sense that you try to operate in this region. And that's why you see that you get a large gain only if you operate in saturation and not in triode. Again, I'm just redoing the same thing in a different way. That's it. Okay. Great. Cool. So now let's, yeah, is this clear till this point? It's nothing new I've introduced, just the same thing that we have looked at from a different perspective. Yeah, so now we have seen what will happen if VDS is not greater than VGS minus VTH. Now let's also look at this condition and see what if you violate it. So let us say VGS is smaller than VTH. What will happen to the current? The current is 0, and what do you call this to be? Cut off. Okay. So which means now if I try to sketch ID versus VGS, so let's say x-axis is VGS, y-axis is ID. Till I reach the threshold voltage, what is the current? And after VTH, assuming it is in saturation, you have the square law dependence on VGS. So it's going to go quadratically like this. Okay. Now let us say I take first derivative of this characteristics with respect to VGS. If I take the first derivative of ID with VGS, what do I get? The transconductance GM, right? Remember, the drain current with respect to VGS is the transconductance, and if I take derivative of this curve, what do I get? Yeah, initially it is 0, and when it is in the quadratic region, if I differentiate, it becomes linear. Fine. Now let's say take the second derivative. What happens? It is 0, and the linear portion becomes. So now you see that there is a discontinuity in the second derivative, right? But in practice, you will see that all device characteristics are such that they are nicely smooth, and all its higher order derivatives are also kind of continuous. Okay, so which means this is not the exact thing that's happening in practice. So it turns out when VGS is less than VTH, the current doesn't abruptly go to 0. The current is still non-zero, and this is often called the weak inversion. So if anyone has taken a course on semiconductor devices, you will understand the mechanism why current is still flowing, but let's not worry about it. So it turns out in weak inversion, that is when VGS is smaller than VTH, the current actually follows an exponential relation. So it is some ID0 e power VGS minus VTH by MVT. And it also has dependence on the drain voltage, so that is captured using this thing. We can do a simple sanity check. So if VDS is 0, what happens to the current according to the equation? 0. Does it make sense? Yeah, I mean, remember that this is a transistor. If the potential difference between drain and source is 0, obviously there cannot be any current. So at least that sort of makes sense. And other thing is, if okay, one thing is here, VT is not the threshold voltage, it is the thermal voltage, KT by Q. K is what? Boltzmann constant. T is temperature in Kelvin, and Q is electronic charge. Hopefully you have seen this before. At room temperature, roughly it is about 25 millivolts. Okay, 25.6 millivolt, but it's okay. And M is a non-ideality factor. It can be anywhere between 1 or 2. Let's not worry about it so much. And if let us say I choose the drain to source voltage to be much greater than M times VT, what happens to this term? Yeah, if VDS is much greater than this kind of drops to 0. So this entire term becomes 1. So in that case, I can say that my drain current is some ID0 e power VGS minus VTH. So as you see, if I have the drain voltage to be sufficiently greater than something, the current no longer seems to depend on the VDS. This is similar to what you had for saturation here, right? Here also, after a particular VDS, the drain current doesn't depend so much on VDS. So something similar is happening here. So once again, let's do the same thing. If I have a delta VGS here, this is going to change. So, and how will, again, this will be related in a linear fashion. So once again, if I were to model this functionality using an equivalent circuit, how will it look like? I know that any change in VGS results in a drain current. If I were to model this using some equivalent circuit, how will it look like? Okay, it's the same thing. Okay, we have gate, drain source. It's the same old, right? Any change in VGS is reflected as an equivalent current here. And of course, although I have eliminated it completely, in practice, VDS still plays a role. So the effect of VDS, you include it using the same R0. Okay. This clear? So now let's quickly do this. See, remember that as we just saw, whether we are in this region or in the earlier region, after some particular value of VDS, the current stops responding to VDS roughly, right? Whether it is in this weak inversion or in this saturation, and typically this saturation is technically referred to as strong inversion, by the way. Okay. So whether you are in strong inversion or weak inversion, after a particular VDS, the drain current stops responding to VDS, and you are operating in this kind of region, which is where you want your two-port network to be biased at, right? So with respect to using an amplifier, you can either use your transistor in this strong inversion or in this weak inversion. So as a designer, now you have two choices. So what would you do? You have two choices. So before choosing, what would you do? You try to at least get a comparison of the pros and cons of each. So let's quickly do that. Again, we'll use the intrinsic gain as a metric. Okay, and as we just saw, the R0 is going to be really large, right? Because the drain current is roughly constant. So let's not worry about R0. In either weak inversion or the earliest strong inversion, R0 is going to be large. So let's only compare GM. So here, if I take the derivative of the current with respect to VGS, I think in the interest of time I will directly give it. You will find that this is some ID by M times VT. Okay. So now what I will do is I will quickly copy what we had for strong inversion and compare the results. This is what we saw for strong inversion. So I'll use the last expression for GM, 2 times ID by VGS minus VTH. Okay. Let's make a quick comparison. In weak inversion, let us say the value of M is roughly 1, ideally. Okay. And at room temperature, what is VT? Let's say we take it as 25 millivolts. So in strong inversion, I will rewrite it as ID by VGS minus VTH by 2. Now, if it is in strong inversion, remember VGS is much greater than VTH. So VGS minus VTH will typically be a large number. Okay, and for example, I will say this term is roughly 100 millivolts or so. In fact, in practice, this can be even higher. VGS minus VTH can be 300 millivolt, 400 millivolt, anything. Just an example, I have taken 100 milli. So if for the same drain current ID, in which case do you think I get a larger transconductance? In strong inversion or weak inversion? Here it is 25 millivolts, whereas here it is 100 millivolts. So obviously in weak inversion is where you get the higher transconductance. So what I'll do, I'll go to next page. I'll just quickly rewrite it. GM in weak inversion, as we saw, was ID by M times VT. GM in strong inversion was ID by VGS minus VTH by 2. For the same drain current, the weak inversion has a larger GM. Okay? And the parameter that we use for defining this is this ratio of GM by ID. Okay? So this essentially says what is the maximum GM I can squeeze out of a transistor when I bias it at a particular drain current. The other way to interpret it is as a metric of power efficiency. That is, to get a particular GM, how much should be the current I should be consuming in the transistor. And as we saw, do you think the GM by ID is higher for weak inversion or strong inversion? Weak inversion. So simply from power efficiency point of view, which is better? Weak inversion. So then that begs a question. So then why don't we use all our circuits to be biased in weak inversion? So in all your courses, why you were taught to bias your transistor in this saturation or strong inversion? So something must be, there should be some con to this. Right? And it turns out there are a couple of things, right? So first of all, when you are operating in weak inversion, do you think the current is large or small? First of all, current is small. Second of all, for the same current, right? Let us say I am looking at the same current. I started in strong inversion now. I want to move to weak inversion. That is, for the same current, I want to bias my transistor in weak inversion. I should be increasing VGS minus VTH or reducing VGS minus VTH? I should reduce. Let us say I am using a constant current to bias a transistor. For this current, for VGS minus VTH to reduce, what would you do? What is the thing you can change in the equation? Huh? VGS is not so much, right? Increase? That's the only thing. For the same current, if I were to keep reducing VGS minus VTH, this fellow has to increase. Is this clear? If W by L increases, what can you say about the capacitances associated with the MOSFET? Again, without knowing anything about the transistor, larger area means larger capacitance. That's all. So let me write it here. So what it means is, first of all, I have a smaller ID, and also for a given ID, my WL ratio will be large. So which means the parasitic capacitances will be large. Okay. So if I have larger capacitances and smaller current, do you think the transistor will be able to respond really fast, or it will be slow? The speed will be small. Okay. I'll just say speed reduce. Because remember, in circuits we have delay because we have capacitances. You need finite time to charge or discharge the capacitances. In weak inversion, you typically have small currents to start with. At the same time, the capacitances are larger. So both cumulatively reduce your speed. So this is one reason why you might not want to use your transistor in weak inversion. Because there are other reasons. Each will have its own pros and cons. As and when we go through each topic, we'll kind of make a comparison between the two. But one main reason is speed aspect. So that is why throughout this course, we will assume that the transistor are all biased in saturation. And when I say saturation, it is strong inversion. Remember, saturation happens here also, in weak inversion also. But in this course, whenever I say saturation, I refer to this. And this is where we will be operating our transistors. Okay. So, which means weak inversion is very advantageous if speed is not at all a concern. But what is critical? You can get similar gain, but what is advantage in weak inversion? Power. We are consuming a very small current. Yeah, when power efficiency is the most important parameter, but speed is not, you can use weak inversion. And one important application one important place where this is used is in electronic watches. In fact, the first usage of weak inversion and study of weak inversion was done for electronic watches. And which country do you think is famous for watches? Switzerland, right? All Rolex, Omega, everything is luxury watches are in Switzerland. In fact, it was in Switzerland, all research groups and companies, they extensively worked on weak inversion and made things. And there is this Eric Witos from EPFL. He was one of the early pioneers to study weak inversion operation of transistor, models of transistor, and in fact designed circuits for electronic watches and showed that you can actually design things and make it work. And yeah, just a couple of minutes I'll take. So in digital, everyone has taken some course on digital circuits. In digital, this is often called as subthreshold leakage. Have you heard of this term? Yeah, they call it leakage because they don't want any static power consumption. Ideally, if VGS is 0, you don't want any current. But now because of this, you have some current. So they call it leakage, but strictly speaking, it is not a leakage. It is a well-controlled current that we know, right? So for digital, it is kind of a problem. But as I say, one man's trash is another man's treasure. So a problem is not universally a problem. It is in that particular, aspect, it is a problem. If you are smart enough, you can use a problem to your advantage like this. So just one last thing. So just like how we saw for NMOS, I'm sure you also know we have PMOS. Okay, I'll just write the condition. So VSG is greater than mod VTH, and for saturation you want VSD to be greater than VSD minus mod VTH. Okay, and the drain current is say similar, UPCOXW by L, VSD minus mod VTH. Okay, so the current here flows from source to drain, whereas in NMOS it flows from drain to source. So since the current direction reverses, gate to source becomes source to gate and so on. This is how I will use it. But if you remember things in a different way, please feel free to stick to that, as long as you are comfortable and there is no confusion. But I'll kind of use these things in the course. Okay, and even a PMOS transistor, you'll have all these regions. And the point I want to take, drive home today is this: whether it is NMOS or PMOS transistor, whether it is biased in strong inversion, weak inversion, whatever region, with respect to small signals, it is a voltage controlled current source with an output resistance. That's it. Okay, and not just this, any transistor, starting from the earliest transistor, everything is a voltage controlled current source. Okay, because transistors, people are trying to invent new transistors, and what is the what is the main reason for using transistors? What is the main application of transistors? Yeah, switches, right? So we will continue in the next class. Let's stop.